Jai Hind, myself Ravindra Kumar from EN department. Today I am presenting on the topic voltage regulation of a transformer in the subject fundamentals of electrical engineering, for which the subject code is BEE 101 or 201 depending upon whether it is covered in first SEM or in second SEM. So, in this topic I will be covering about the voltage regulation, that what is the voltage regulation in a transformer, what is the expression for that, I will take the derivation for that and some numerical problem related to that. So, if we say it, first the definition of transformer. Transformer is an AC device which is used to change the high voltage low current AC into a low voltage high current AC and vice versa of it, without changing the frequency on any side. That means the frequency of the two sides that remain same. So, in brief, if we see what are the functions of transformer, number one, it transfers electrical power from one circuit to another circuit. Second, it does so without a change in frequency. Frequency remains same on the two sides. Third, it accomplishes this by the electromagnetic induction, which is the working principle of a transformer that already have been discussed in the other topic, where I have covered transformer in detail about the working principle of transformer, definition, plus construction, plus the ideal transformer and EMF equation of the transformer. All those topics have been covered in that discussion. And fourth function is where the two electric circuits are in mutual inductive influence of each other, there it works. That means the two sides of the transformer or the two circuits in the transformer, that is primary circuit and secondary circuit, or input circuit and output circuit, they are connected with mutual coupling or mutual induction, and that is why a transformer works on the principle of electromagnetic induction. And this is the reason, that is why it is an AC device. Since induction is possible in AC, it cannot be in DC. So, if we see further, what is voltage regulation of a transformer? Efficiency already have been discussed, that I will not discuss here. I will basically be discussing about voltage regulation of a transformer. The output voltage of a transformer varies with the change in load or with the variation in load connected across secondary, even if the input voltage is not changing or that remains constant. This is because of a real transformer, or which we also call practical transformer or actual transformer or transformer, any name, has series impedance connected with this. Full load voltage regulation is a quantity that compares the output voltage at no load with the output voltage at full load, defined by this equation. So, voltage regulation, this term voltage regulation, in short we write it VR, V for voltage, R for regulation. This is by no load voltage at secondary minus full load voltage at secondary upon full load voltage at secondary multiplied by 100 to find it in percentage voltage regulation. For ideal transformer, voltage regulation is 0%. Reason being, in ideal transformer, the winding resistance and leakage reactance is 0, or in other words, I can also say the impedance, series impedance of the winding in ideal transformer is 0. That is why with the flow of current in the winding, there will be no question of voltage drop due to 0 series impedance in ideal transformer for the winding. So, when there will be no voltage drop in the winding, the no load voltage and full load voltage, they will be equal in ideal transformer, and when they will be equal due to no voltage drop in the winding, then there is no question of voltage regulation, or we can say voltage regulation will be 0 in an ideal transformer. that is the reason for it. The formula for voltage regulation, the percentage voltage regulation, this is given by no load voltage in the secondary, this is no load voltage in the secondary minus full load voltage in the secondary upon full load voltage in the secondary. This is full load voltage, not the no load voltage. This is full load voltage, or I can write it V2FL, full load voltage in the secondary. FL means full load and 0 means no load here, and this is given by I2 R02 cos phi 2 plus minus I2 X02 sin phi 2 upon V2, where I2 is the full load secondary current, R02 is the equivalent resistance in the secondary, X02 is equivalent leakage reactance in the secondary, cos phi 2 is the power factor of the load which is connected across secondary, V2 is the terminal voltage at full load in the secondary, V2FL we can write it. Now these two signs, positive sign, this is for lagging power factor, that is written here, positive sign for lagging power factor load, and minus sign is for leading power factor load, this minus sign, this is for leading power factor load. This minus sign, that is for leading power factor load. So accordingly, in the numerical calculations, if it is lagging power factor load connected in the secondary of the transformer, we will use this plus sign here in this formula or positive sign, and if the leading power factor load is connected in the secondary, then we will be using this negative sign here in this formula. That is the important point. And from here we can see some more things. For a transformer, if it is lagging power factor load connected in the secondary, voltage regulation can neither be 0 nor be negative. Since here when it is positive sign, then the addition of two quantities, that cannot be 0 or negative unless any one quantity out of that is negative. But in case of leading power factor load connected across secondary, we are having this minus sign here, that already I indicated here, minus sign for leading power factor load connected in the secondary of transformer. So that time, due to this minus sign here in the formula, the voltage regulation can be 0 also or negative also in when leading power factor load is connected across the secondary. Reason being, if these two quantities I2 R02 cos phi 2 and I2 X02 sin phi 2, they becomes equal, then due to this negative sign the voltage regulation will become 0. Or second case, if I2 X02 sin phi 2 is more than I2 R02 cos phi 2, then with the presence of this negative sign with leading power factor load connected across secondary, the voltage regulation will become negative. So that's why it is important that whenever leading power factor load is connected across the secondary in a transformer, then voltage regulation can either be negative or be 0. Both the things are possible. But with lagging power factor load connected across secondary in a transformer, voltage regulation can neither be negative nor be 0. This is the important point. Now, if we see the derivation for voltage regulation, we can derive this for lagging power factor load. So, we have a transformer which is represented like this. This is a symbolic diagram or symbolic representation for a transformer Now suppose I am using this side as primary, so I will be connecting a voltage supply here V1. In the primary I will be using one subscript with all the quantities since it is primary side. It is having number of turns N1, induced EMF is E1 here. In the secondary it is having induced EMF E2 and terminal voltage is V2. And this is the core of transformer. These two vertical lines, they are representing the core of transformer, and both the sides they are mutually coupled with each other, since both these sides or both these coils or windings, they are wound over this common magnetic core. I again repeat the symbols. V1 is the supply voltage which is connected across primary or input voltage also we can say. E1 is the induced EMF in primary. E2 is the induced EMF in secondary. V2 is the terminal voltage across secondary. Now, as per the definition of voltage regulation, we can write voltage regulation is E2 minus V2 upon V2 into 100 in percentage. Why? Since voltage regulation is defined as change in the secondary terminal voltage from no load to full load at a given power factor with primary voltage held constant. So, no load voltage, when there is no load connected across secondary, that time this V2 and E2 are equal. So, E2 becomes no load secondary terminal voltage. When we are connecting some load impedance across secondary, then there will be some current passing through secondary, due to which voltage drop will take place in the secondary, and this terminal voltage V2 will be different from E2 that time. So, V2 represents full load secondary voltage, secondary terminal voltage, and this voltage regulation is expressed with respect to full load secondary terminal voltage V2. So, that is why the voltage regulation is E2 minus V2 upon V2, and if we take it in percentage, so it will be given by E2 minus V2 upon V2 into 100, which is representing the percentage voltage regulation in a transformer. So, how can we derive the expression for it for a lagging power factor load? We know the equation in a transformer, that is given by voltage equation in a transformer E2 equal to V2 plus I2 into RE2 plus JXE2. This is the voltage equation of a transformer. In this, the various symbols are: E2 is no load secondary terminal voltage, which is also known as induced EMF in the secondary. V2 is the full load terminal voltage of the secondary when full load connected across secondary. I2 is full load secondary current. RE2 is equivalent resistance in secondary, which is given by RE2 is R2 plus R1 dash, where R2 is secondary winding resistance and R1 dash is primary winding resistance referred or transferred to secondary, which is given by R2 plus R1 into N2 upon N1 square. Similarly, XE2, this is the equivalent leakage reactance in secondary, which is given by X2 plus X1 dash, and that can further be written as X2 plus X1 into N2 upon N1 square, where X2 is leakage reactance in secondary winding, X1 is the leakage reactance of primary winding, N1 is number of turns in the primary winding, N2 is number of turns in the secondary winding, and N2 upon N1, that is also known as transformation ratio of a transformer, which is represented by small k. It is given by N2 upon N1. So, that is the method for finding RE2 and XE2. Now, if we draw the phasor diagram for a lagging power factor load in a transformer. We can draw it, and from the help of that we can find the or we can derive the expression for voltage regulation of a transformer when lagging power factor load is connected across the secondary of a transformer. So, we can see it. How can we do it? From the equation, as already I have written in the last slide or previous slide, E2 equal to V2 plus I2 into RE2 plus JXE2. Suppose I am using V2 as a reference phasor. So, V2 will be taken like this. This is the reference phasor. Now, we are having lagging power factor load connected in the secondary. That means to say the load current I2 in the secondary, that will be lagging by some angle from load voltage V2. So, I2 will be here lagging by some angle from V2. Suppose this angle is phi 2. This is lagging angle. Cosine of this angle phi 2, that is cos phi 2, that will be known as power factor of the load, and that will be lagging power factor since load current I2 is lagging by angle phi 2 from load voltage V2. Now, for obtaining this equation in the phasor diagram, how can we do it? I2 RE2, this is the voltage drop in resistance RE2. So, it will be in phase with I2. So, when I will connect it with V2, so I will take a parallel line with I2. This is I2 RE2. Now, I2 XE2, it will be leading by 90 degree from I2. Since XE2 is leakage reactance, equivalent leakage reactance in secondary of transformer, and this leakage reactance is basically inductive reactance. Why we call it leakage reactance? Due to leakage flux in transformer, but basically it is inductive reactance, and we know in an inductance the voltage leads the current by 90 degree or current lags the voltage by 90 degree anyway. So, I2 XE2, this is the voltage in the inductive reactance which is leakage reactance in the secondary. So, this voltage will be leading from I2 by 90 degree. So, that way it will be like this. This is I2 axis since it is parallel to I2. So, I2 XE2 will be leading by 90 degree from I2. This is I2 XE2. This angle is 90 degree leading. And now, the phasor addition of V2, I2 RE2 and I2 XE2, that is equal to E2. Now, what can we do? We extend this line like this. From here we draw the perpendicular line. Similarly, here we draw a horizontal line. That way we complete this diagram, and then we can derive the expression for voltage regulation. Now, I mark the terminal names. Suppose this terminal is OA. This is this I take as B. This terminal is C. This terminal is suppose D, and this terminal is suppose P, Q, and this terminal is suppose F. So, now this angle is delta angle between E2 and V2, that we can see from diagram, and this angle delta is a very small angle. Delta is a very small angle. Now, from this diagram we can see this OD equal to OF cos delta. From this right angle triangle ODF, OD equal to OF cos delta, and since delta is a very small angle, so cos delta will be very near to 1. Cos delta is very near to 1. Since when delta is 0, cos 0 is 1, and since delta is a very small angle, so cos delta can be approximately very near to 1. So, I can write OD is approximately OF, and OD is E2 and OF is OF is V2. So, OD also becomes OF, that is V2. So, now I can write OD equal to, from the diagram, it is equal to OA plus AC plus rather than AC, I will be taking it AB. Why? That will be clear in the further discussion. OA plus AB, I make it clear. OA plus AB plus BD. That is very much clear from this diagram. OD equal to OA plus AB plus BD. Now, this can be written OD is V2, OD is E2, not V2, since OD equal to OF and OF is E2. So, this is E2, not V2. So, I write it here, OD is E2, OA is V2 plus AB. AB, this angle is phi 2, this angle is also phi 2, since I2 RE2 is in parallel with I2. So, AB becomes I2 RE2 cos phi 2 plus BD. BD is equal to BD, that is also equal to this PQ. From here to here, this is PQ. And from this right angle triangle, we can find the value of PQ. When this angle is phi 2 and this angle is since 90 degrees, so this angle becomes 90 minus phi 2. And when this angle is 90 minus phi 2, this angle is also 90 minus phi 2. So, that is why this is 90 minus phi 2. So, this angle becomes phi 2. And when this angle is phi 2, so PQ becomes I2 XE2 sin phi 2 from this right angle triangle PQF. PQ is equal to PF sin phi 2, or and PF is I2 XE2. So, that is why PQ becomes I2 XE2 sin phi 2 and PQ equal to BD. So, in place of BD, I can also write the value of PQ, which is I2 XE2 sin phi 2. So, from here the voltage regulation will become percentage voltage regulation, which is no load voltage in the secondary, no load terminal voltage in the secondary, that is E2, minus full load voltage secondary terminal voltage V2 upon full load secondary terminal voltage V2 into 100. So, this becomes I2 RE2 cos phi 2 plus I2 XE2 sin phi 2 upon V2 into 100. So, that is how we derive the expression for voltage regulation in a transformer for a lagging power factor load, and the important point here we get plus sign with lagging power factor load. The symbols already I have defined. I2 is full load secondary current in the secondary side, cos phi 2 is load power factor, V2 is full load secondary terminal voltage, RE2 is equivalent resistance in the secondary, XE2 is equivalent leakage reactance in the secondary. The values of these that already have been defined, RE2 is given by this expression, XE2 is given by this expression. Now, the important point is, if we derive this expression of voltage regulation for a leading power factor load, then we will be getting negative sign here in place of positive sign. And from that we can see, for a leading power factor load, due to the negative sign here in place of positive sign, the voltage regulation can either be 0 or negative, both conditions may be possible. for a leading power factor load when we are finding voltage regulation. But for lagging power factor load, due to the positive sign, this positive sign, voltage regulation can neither be 0 nor be negative for lagging power factor load connected across secondary regarding voltage regulation. Another important point, as already I discussed in the very beginning, that for a ideal transformer, voltage regulation is 0. This can also be seen from here, from the expression of voltage regulation. This is the expression for voltage regulation that we derived for a lagging power factor load. In an ideal transformer, winding resistance and leakage reactance both are 0 when we are taking ideal transformer. So, that time Re2 and Xe2 both will be 0 for ideal transformer, and when they are 0, the voltage regulation will also be 0 for an ideal transformer. So, that is the reason, or in other words, we can also say with the connection of load impedance across the secondary in an ideal transformer, there will be no voltage drop whatever is the current in the secondary, but no voltage drop due to the 0 winding resistance and leakage reactance. That is why no load terminal voltage and full load terminal voltage, they will be equal, and when they will be equal, this voltage regulation will become 0 since E2 and V2 will be equal. So, voltage regulation will be 0 for an ideal transformer. So, these are some important points related to voltage regulation, that for ideal transformer voltage regulation is 0. For lagging power factor load, voltage regulation can never be 0 or negative. For leading power factor load, voltage regulation can be 0 or negative. Both conditions are possible. So, this is about voltage regulation. If we take some numerical example for this, what can be there in that? Suppose we are given a transformer having voltage rating 3300 to 110 volt. We are given the data, R1 is suppose 0.1 ohm, R2 is 0.01 ohm suppose, then X1 is suppose 0.5 ohm, X2 is 0.05 ohm, and we are connecting a lagging power factor load or leading power factor load, anything, suppose leading power factor load 0.8 leading, and we are to find voltage regulation of the transformer. Suppose the KVA rating of transformer is 1 KVA. Then how can we find the voltage regulation? First, I will find full load current I2. That will be given by voltage rating, that is 1 KVA, that is 1 into 10 raised to power 3 VA upon voltage 110 volt. That is current I2, full load current. Similarly, I will be finding Re2, which is R2 plus R1 into N2 upon N1 square. So, R1 and R2, that is known to me, and N2 upon N1 will be V2 upon V1, that is 110 upon 3300, that is N2 upon N1. So, that I will place in this formula. Similarly, Xe2 is X2 plus X1 into N2 upon N1 square, and then I will apply it in the formula for voltage regulation for a leading power factor load, which is given by I2 Re2 cos phi 2 minus I2 Xe2 sin phi 2 upon V2 into 100. So, I2 value that already I found, Re2 value that can be found from this formula, Xe2 value that can also be found from this formula, cos phi 2 is given 0.8, sin phi 2 can be calculated, that will become 0.6, minus sign here due to leading power factor load which is given to us, V2 is 110 volt. So, after putting these values here in this expression of voltage regulation, I can calculate the voltage regulation of the transformer. So, that way we can find the voltage regulation of a given transformer for given data and related to lagging or leading power factor load. That is all in this. In the next discussion, I will be discussing some more topics related to transformer. Thank you for this.